Imagine deploying just a single line of code that accidentally freezes the credit cards of a million innocent people who are just trying to buy a cup of coffee.
Right.
Or, pushing an update to an autonomous vehicle system, and suddenly it completely forgets how to read a basic traffic sign simply because the camera lens was swapped out for different model.
Yeah, that's the nightmare scenario.
It really is, because when we discuss traditional software engineering, the expectations are they're largely deterministic. You write a function, it executes the logic, and if the system crashes, well, you open an error log, find the stack trace, and point directly to line 42 to identify the bug.
Exactly.
It's predictable. But stepping into the architecture of global scale machine learning, that comforting determinism it vanishes.
It completely evaporates, yeah.
Right. The systems become probabilistic. You are no longer writing instructions. You're like designing environments where algorithms learn to make their own rules.
Right. And that transition from deterministic logic to probabilistic systems, I mean, it fundamentally changes the entire engineering discipline.
How so? Like in a practical sense?
Well, an algorithm might compile perfectly, right?
Yeah.
The server might report zero downtime, and the latency could be well within your service level agreements.
So the dashboard is all green.
Everything looks perfectly fine to a traditional software engineer.
Right.
Yet the model itself could be silently hemorrhaging millions of dollars in bad predictions.
Mm-hmm.
The code isn't broken, but the system's mathematical grasp on reality has basically fractured.
Wow.
Yeah, and navigating that distinction requires an entirely different architectural vocabulary.
Which brings us to what we're doing today. Welcome to the deep dive. Today, we are undertaking a really highly specific mission for you. We've got our hands on a blueprint, basically a deck of 54 highly detailed scenario slides used for the Google Cloud Professional Machine Learning Engineer certification.
Which is an incredible resource.
It really is, because these aren't, theoretical musings about artificial general intelligence taking over the world. These are the exact high-stakes architectural constraints Google uses to test whether an engineer can deploy massive AI systems without, tearing down the underlying infrastructure.
It serves as a masterclass in modern ML engineering principles.
Hmm?
I mean, the scenarios force you to look at a real business problem, weigh the constraints of compute budgets, latency requirements, data scale, and then actually choose the optimal path.
It's an exercise in extreme pragmatism.
Exactly.
Okay, let's unpack this, because I want to treat this deck like a Michelin star chef's secret recipe book.
I like that analogy.
Right. By reverse engineering the quote-unquote correct architectural choices in these scenarios, we can extract the core philosophy of how top-tier engineers actually wrangle petabytes of data.
And how they train models without burning through $1 million of cloud compute in a weekend.
Exactly, and keep these probabilistic systems anchored to reality. So let's start at the absolute bedrock, which is the data foundation.
Makes sense. Where are we starting?
There is a scenario here involving a massive retail company. They have a data set stored in Vertex AI containing historical sales data from multiple store locations, and it includes timestamps for every single transaction.
Okay, classic time series setup.
Right. And they are opening a brand new store and need a model to predict its future sales. The architectural hurdle here isn't the algorithm itself. It's how to physically partition the data into training, validation, and testing sets.
Yes. And this scenario specifically tests your defense against one of the most destructive phenomena in machine learning, which is time leakage.
Time leakage. Okay, because my initial instinct, assuming I have this massive data set of retail transactions, is to treat it like a giant deck of cards.
Which is what most people do initially.
Yeah. I would just shuffle the entire data set, randomly carve out 70% for the model to train on, maybe 20% to validate its learning, and hold back 10% for a final test. It's statistically random, so it should prevent the model from memorizing any specific chunk of data. Why does this blueprint consider a random shuffle a catastrophic failure?
Well, because shuffling the deck ignores the fundamental physics of the data you are trying to model.
The physics.
Yeah, time series data is bound by autocorrelation, meaning the value of a sale today is mathematically related to the value of a sale yesterday.
Okay, that makes sense.
So if you execute a purely random split, you are taking data from, say, December 2023, placing it in the training set, and then placing data from October 2023 in the testing set.
Oh, I see. You are inadvertently letting the algorithm look into the future.
Exactly. You are literally feeding it a sports almanac from the future.
Like Back to the Future Part 2.
Yes. The model's entire objective during training is to minimize its error. If it has access to future trends like a massive spike in holiday sales, it will just use that future information to perfectly, quote, predict the past.
So it cheats.
It cheats perfectly. And when you run your final test, the model will output a near-perfect accuracy score.
And the engineering team might pop champagne and deploy it to the live servers.
Right? But tomorrow, when it is actually asked to predict next week's sales, it will completely collapse. It no longer has access to its time machine.
Because tomorrow hasn't happened yet.
Exactly. So the blueprint mandates a strict chronological split. You train on January through September, you validate on October, and you test on November. The arrow of time must flow in only one direction.
Okay, so we solved the time travel problem. Our model can't see the future. But there's another scenario here that highlights how a model can still instantly die the second it hits the live internet, even with perfect time splits.
Let me guess. Train, serve, skew.
You got it. It involves a custom TensorFlow model where the engineering team needs to apply complex mathematical transformations to the data before it enters the model.
Standard pre-processing.
Right. But they need to do this during the training phase and also during the live serving phase when real users are interacting with it. And the blueprint warns against this train-serve skew.
Yeah, train-serve skew is arguably the most insidious degradation an ML system can experience, mostly because it rarely triggers an actual software alert.
Let's ground this for a second. What physically causes the skew between a training environment and a live production server?
Okay, consider a feature like the square footage of a house for a pricing model.
Okay.
In the research phase, a data scientist might be working in, say, a Python notebook. They notice the raw database stores the area in square meters. So they write a simple pandas function to multiply the value by 0.0929 to convert it to square feet.
Just standard math.
Right. They train a highly accurate TensorFlow model on this converted data. Once approved, the model artifact is handed over to the back-end software engineering team to integrate into the live website.
And the back-end team is likely operating in a completely different language, right? Perhaps building the live serving infrastructure in Java or Go.
Exactly.
Yeah.
That's where the problem starts. The back-end engineer looks at the documentation, sees they need to convert square meters to square feet, and writes their own conversion logic in Java. Perhaps they decide to divide by 10.764 instead of multiplying.
But mathematically, the logic is sound, right?
Mathematically, yes. But at the machine level, floating point arithmetic behaves differently across different languages and memory architectures. Microscopic rounding errors begin to accumulate.
Oh, wow.
Or, in a more common scenario, the back-end team just slightly misinterprets the data scientist's really complex natural language processing logic when they're rewriting it.
So the live model begins receiving input data that looks, well, alien compared to the precise mathematical distributions it was trained on.
Yes. It starts spitting out inaccurate predictions, but the software infrastructure is functioning perfectly, so no alarms go off.
It's failing silently. The blueprint solves this by recommending a very specific pipeline, Apache Beam running on Dataflow, utilizing TensorFlow Transform. Let's break down the mechanics of why this specific triad of tools eliminates the skew.
The magic really lies in how TensorFlow Transform handles the preprocessing logic. Instead of treating the data transformation as a separate script that needs to be manually rewritten for the live environment, TensorFlow Transform executes your Python preprocessing code and exports a locked computational graph.
A locked graph. What does that mean practically?
It means it's an immutable, serialized artifact of the exact mathematical operations required. You physically attach this graph to the front of your trained model.
So it's essentially a hardware seal.
That's a great way to put it.
Instead of giving the live engineering team a list of instructions on how to prep the incoming data, you just hand them a sealed black box processing unit that is permanently welded to the model.
Yes, and the live data flows to the exact same computational graph that the training data flowed through. It guarantees byte-for-byte consistency, regardless of what language the surrounding web server is written in.
That is brilliant. And where does Apache Beam fit into this?
Well, Apache Beam provides the unified programming model to execute that graph. Beam is totally agnostic to whether it is processing petabytes of historical bash data from a warehouse during training or processing just a single real-time streaming event from a live user.
It doesn't care about the scale.
Exactly. Dataflow simply acts as the underlying managed server infrastructure that automatically scales to handle either workload. You write the pre-processing logic once, and the infrastructure guarantees identical execution across both the research and production environments.
Speaking of scaling infrastructure, there is a fascinating bottleneck outlined in a scenario regarding Vertex AI feature store.
Well, this is a classic operations problem.
It really is. So an engineering team deploys a model that relies on the feature store for live online serving. However, every night they run a massive batch ingestion job to update the store with fresh data from the warehouse.
To keep the features current.
Right. But when this batch job runs, the CPU utilization on the feature store spikes to absolute maximum capacity, and the latency for the live online serving skyrockets. The web application essentially freezes for the users.
Yeah, to understand the architectural failure here, we have to look at what a feature store physically is.
Okay, what is it?
It is a dual-engine database. It solves a massive redundancy problem in enterprise machine learning. Instead of 50 different data science teams independently calculating, say, the user's 30-day rolling average spend, the data engineering team calculates it once and stores it centrally as a curated feature.
Oh, that makes sense. But retrieving that feature requires two entirely different database interaction patterns, doesn't it?
Precisely. The feature store handles online transaction processing, or OLTP, which requires sub-millisecond latency.
Because there's a human waiting.
Right. When a user loads the checkout page, the live model needs to instantly fetch their 30-day average spend to recommend a coupon. If that retrieval takes 500 milliseconds, the user's browser hangs, and they just abandon the cart.
But then you have the batch job.
Exactly. Simultaneously, the feature store handles batch ingestion. Millions of newly calculated records arrive from the data warehouse and must be written to disk. These two operations violently compete for the exact same underlying CPU and memory resources.
Now, a common assumption with modern cloud architecture is that autoscaling just solves this, right?
A dangerous assumption, yeah.
If the CPU spikes because a massive batch job begins, shouldn't the cloud provider's autoscaler automatically detect the load, provision more nodes, and distribute the traffic before the web application freezes? Why does the blueprint explicitly say we cannot rely on reactive autoscaling here?
Because provisioning physical infrastructure actually takes time,
Even in the cloud.
even in the cloud. When the batch job hits, the CPU utilization goes from 20% to 100% almost instantly. The autoscaler's monitoring daemon detects the sustained spike, evaluates the scaling policy, and then requests new virtual machines from the cloud provider's control plane.
Okay.
Then the provider allocates the hardware, boots the operating system, initializes the database software, and integrates the new nodes into the load balancer network. That entire sequence might take 3 to 5 minutes.
3 to 5 minutes. And in high-frequency trading or global e-commerce, 5 minutes of latency translates to millions of dollars in lost revenue.
Exactly. The system is reacting to the fire after the building is already burning.
So what's the solution?
The Blueprint solution emphasizes proactive operational management over just blind reliance on automated cloud magic. You know exactly when the daily batch ingestion job is scheduled to run, say, midnight. The correct architectural choice is to script an API call to manually increase the online serving nodes at, say, 11:55 p.m.
So you deliberately over-provision the infrastructure.
Yes. You smoothly absorb the incoming computational shockwave, and then you scale it back down once the ingestion completes.
It's a really good reminder that ML engineering requires a deep understanding of bare metal server physics. We see this tension between data formats and infrastructure in another scenario, too.
Which one?
A company is migrating to Google Cloud and possesses terabytes of structured data sitting in a cloud storage bucket, and it's saved in the Avro format.
Okay, Avro files.
They need to perform heavy analytics, engineer new machine learning features from this data, and eventually host those features for online prediction. The blueprint dictates that the optimal path is to ingest the Avro files directly into BigQuery, execute SQL to create the features, and store the results in a separate BigQuery table.
Yeah, the choice of where to physically land the data dictates the entire velocity of the machine learning lifecycle.
Why is Avro a problem here?
Well, Avro is an excellent format for data serialization and transport because it's really compact and it carries its own schema, but it is fundamentally a flat file.
Okay.
You cannot efficiently execute complex mathematical aggregations across millions of flat files just sitting in an object storage bucket. You must move the data into an actual compute engine.
Now, some engineers might lean towards a highly robust relational database like Cloud Spanner for this, but the blueprint rejects that. Why is BigQuery the mandatory choice here?
It comes down to the fundamental difference between row-based and columnar databases. Spanner is an incredible engineering feat for global synchronous OLTP workloads.
Like banking.
Like banking. If you are building a banking ledger where a financial transaction must be instantly and perfectly recorded across 3 continents, Spanner is absolutely the tool. It stores data in rows, which is highly efficient when you want to look up a single user's complete profile.
But feature engineering rarely looks at a single user in isolation, right?
Exactly. Feature engineering is an online analytical processing, or OLAO, workload. You aren't asking for user 133's profile. You are asking the database to calculate the standard deviation of purchase amounts for every single user in Europe over the last 5 years.
That's a massive query.
Right. BigQuery is a columnar data warehouse. It stores every user's purchase amount contiguous on the physical disk. When you run an aggregation query, it doesn't have to load massive amounts of irrelevant row data into memory. It just scans that single column.
Oh, that makes sense.
A columnar architecture can scan petabytes of data and return an aggregation in seconds, something that would cause a traditional row-based database to just grind to a halt. Furthermore, BigQuery utilizes a serverless architecture.
Meaning no clusters to manage.
Yes. It instantly allocates thousands of distributed compute slots behind the scenes to execute your SQL, meaning your data analysts can build complex ML features using standard SQL without managing any clusters at all.
Which brings us to a massive fork in the road. We've established chronological splits, we've locked our preprocessing graphs to prevent skew, we are proactively managing our feature store nodes, and we have landed petabytes of structured data into a columnar warehouse. The foundation is poured.
The hard part is done. Well, part of the hard part.
Exactly. But now how do we actually train the neural network? The traditional approach is to pull that data out of the warehouse, load it into an array of GPUs, and write thousands of lines of custom TensorFlow code. Yet, the overarching philosophy in this blueprint aggressively pushes engineers to avoid writing code whenever possible, prioritizing managed services.
Yes, the paradigm shift here is really about the gravity of data.
The gravity of data.
Historically, compute was the central hub, and you move data to the compute. But moving terabytes of data over a network is incredibly slow. It introduces severe security vulnerabilities during transit, and it incurs massive egress costs.
So it's expensive and risky.
Extremely.
Yeah.
The modern architectural philosophy is to bring the compute to the data.
This is heavily emphasized in a scenario involving a gaming startup. They possess terabytes of structured gameplay and user metadata sitting in their warehouse. They want to build a machine learning model to recommend new games to users, and they explicitly need the solution to require the least amount of coding.
Standard startup constraint.
Right. The blueprint's answer is to use BigQuery ML to train a matrix factorization model directly inside the data warehouse.
BigQuery ML is fascinating because it allows an engineer to train complex machine learning models using standard SQL syntax. You literally just type create model and define your parameters.
Wait, really? Just create model?
Literally. The database engine itself handles the provisioning of the underlying compute, the memory allocation, and the distributed training algorithms. You never extract the data.
That's wild. Let's drill into the specific algorithm recommended for this scenario, though. Matrix factorization. Why is this the undisputed king of recommendation engines, and how does it actually map user behavior to game recommendations mathematically?
Matrix factorization relies on the concept of latent features.
Correct.
Imagine a massive grid. The millions of rows represent your users, and the thousands of columns represent every game on your platform. The intersecting cells contain the rating a specific user gave a specific game.
Okay, I can visualize that.
But in reality, this matrix is incredibly sparse because a single user only plays a fraction of a percent of the available catalog.
Right. The vast majority of the grid is completely empty. The algorithm's job is to predict what numbers belong in those empty cells.
Exactly. Matrix factorization solves this by mathematically decomposing this massive, sparse matrix into 2 much smaller, dense matrices, a user matrix and an item matrix.
How does that help?
Through gradient descent, the algorithm learns to assign a vector of numbers embeddings to every user and every game. These embeddings represent hidden or latent traits. The algorithm might discover that one specific mathematical dimension strongly correlates to, say, fast-paced multiplayer shooters, while another correlates to narrative-driven puzzles.
But the algorithm doesn't actually know what a shooter or a puzzle is, right? It just recognizes the mathematical covariance.
Exactly. Users who highly rate game A also tend to highly rate game B, so those games get clustered together in the vector space.
So to predict a user's rating for a game they haven't played yet.
The database simply calculates the dot product of that user's embedding vector and the game's embedding vector. BigQuery ML can execute this matrix decomposition across terabytes of data with a single SQL query.
Which drastically reduces the engineering overhead compared to building a custom distributed recommendation system from scratch.
Absolutely.
We see this exact philosophy applied to time series forecasting, too. Another scenario asks how to predict sales for short life cycle retail products with minimal effort. The required architecture is BigQuery ML utilizing the ARIMA Plus model.
Right. RMO stands for Autoregressive Integrated Moving Average.
That's a mouthful.
It is. It is a foundational statistical method for forecasting time series. The autoregressive component models the relationship between a current observation and its past values. The moving average models the error in the system.
And the integrated part.
The integrated component applies differencing to make the data stationary, meaning its statistical properties like mean and variance don't change over time, which is an absolute requirement for accurate forecasting.
But tuning an ARIMA model is notoriously tedious for a data scientist. You have to manually test for stationarity, determine the order of differencing, and painstakingly account for external variables.
Which is exactly where the PLUS and BigQuery ML's ARIMA Plus comes in. It automates that entire statistical pipeline.
Oh, I see.
Yeah, before the error model even runs, the managed service automatically detects and scrubs data anomalies. It identifies sudden spikes and interpolates missing values. Most importantly, it automatically extracts seasonality.
Seasonality, like summer versus winter.
Yes, or even day of the week. If you are forecasting retail sales, the algorithm mathematically isolates the weekly fluctuations like increased traffic on Saturdays as well as annual holiday trends without the engineer having to manually code weekend or December as explicit features.
So it is effectively democratizing advanced statistical forecasting. You can execute high-level data science using declarative SQL. It's like having a built-in microwave in your fridge. You don't even have to take the food out to cook it.
That is a very apt analogy.
But the blueprint also draws a hard line on when managed services fail. It aggressively tests the engineer's ability to know when to graduate from an automated tool to a custom-built architecture. Let's examine a scenario involving computer vision.
Okay, let's hear it.
An engineering team is tasked with identifying traffic signs from dashboard camera footage. They have 100,000 images, and the prompt includes a really critical detail. The images have already been tightly cropped by a data pipeline to show only the traffic sign.
Ah, that's the key.
The blueprint dictates using Vertex AI AutoML for image classification. It explicitly rejects building a custom TensorFlow object detection model.
Yeah, the distinction between classification and object detection is fundamental to managing compute costs and latency. Object detection algorithms like YOLO or faster RCNN are computationally heavy because they have to solve two distinct mathematical problems simultaneously.
What are the two problems?
First, they must perform bounding box regression. That means scanning the entire high-resolution image to locate where objects exist and drawing a box around them. Second, they must run classification on the pixels inside that box to determine what the object actually is.
So if I hand the model a raw, wide-angle 4K image of a busy highway, it needs object detection to hunt down the stop sign in the top right corner.
Yes. But the prompt specifies the data engineering team has already cropped the images. The where is it problem has been solved entirely outside the model.
Oh, because the bounding box is essentially the entire image now.
Therefore, deploying an object detection algorithm is a massive waste of computational resources. You only need to solve the what is it problem.
You simply need image classification, which just outputs a probability distribution across categories like 99% stop sign, 1% yield sign.
And because image classification is a highly standardized problem, Vertex AI AutoML is the optimal tool here. You provide the labeled dataset, and AutoML utilizes neural architecture search.
What's that do?
Behind the scenes, Google's infrastructure spins up hundreds of different convolutional neural network topologies, trains them simultaneously on your dataset, evaluates their performance, and automatically selects the most efficient architecture.
So writing custom TensorFlow code to manually tune convolutional layers for a standard classification task is just...
It's an inefficient use of a highly paid engineer's time.
I understand the logic. AutoML acts as a high-speed optimization engine for standard problems. But then we hit a scenario where AutoML is explicitly the wrong choice.
Okay, let's hear this one.
A company needs to estimate industrial power consumption based on tens of millions of sensor records generated daily. They need a system that scales smoothly. The blueprint rejects AutoML and dictates that the engineer must write a custom TensorFlow regression model and optimize it using Vertex AI training. Why does the automation fail here?
It fails due to the sheer scale and the extreme specificity of the telemetry.
Because there's so much data.
Tens of millions of sensor records daily represent ultra-high-frequency time series data. While AutoML is exceptional at finding general patterns, it builds architectures designed to be broadly robust. When you are processing billions of rows of proprietary industrial sensor data every month, a broadly robust model is highly inefficient.
Right, the compute costs would be astronomical.
Exactly. At that extreme scale, you need absolute granular control over every tensor operation. An engineer must write a custom TensorFlow model to precisely dictate the depth of the neural network, the specific activation functions, and the memory management protocols to shave milliseconds off the inference time.
It's custom tuning.
A custom architecture allows you to optimize the trade-off between mathematical precision and computational cost in a way that an automated neural architecture search algorithm simply cannot infer.
But they still use Vertex AI training.
Yes. Vertex AI training allows the engineer to bring that highly tuned custom code, but still relies on the managed cloud infrastructure to physically distribute the training workload across massive clusters of GPUs. You write the bespoke logic, but you don't manage the bare metal servers.
Okay, that makes sense. Now, here's where it gets really interesting. We have spent considerable time discussing tabular data, the neat, organized rows and columns of databases and sensors, but the vast majority of human data is unstructured. It's messy.
Oh, completely chaotic.
It's audio recordings, blurry photographs, dense PDF documents. The blueprint outlines a specific strategy for handling this unstructured chaos by leveraging pre-trained APIs. There is a scenario involving a customer service center. They need to transcribe long-form telephone calls. The recordings are saved at an 8 kilohertz sample rate, and the files are roughly 5 minutes long.
This scenario is a classic trap. It's designed to test an engineer's understanding of signal processing and network protocols. Well, the incorrect options strongly suggest utilizing audio engineering tools to upsample the 8 kilohertz audio to 16 kilohertz before sending it to the machine learning API, under the assumption that higher quality audio yields better transcription accuracy.
I mean, it sounds incredibly logical. If you want an AI to understand speech better, give it a higher resolution file. Why is that an architectural mistake?
Because of the Nyquist-Shannon sampling theorem.
The what?
The Nyquist-Shannon sampling theorem. Basically, the original audio was captured at 8 kilohertz, which is the standard bandwidth for traditional telephony. Upsampling that file to 16 kilohertz does not magically recover the high-frequency acoustic data that the original telephone microphone failed to record.
Oh.
You're simply taking the existing sound waves and mathematically stretching them across a larger file size, filling the gaps with interpolated noise.
So you are doubling the file size, doubling the network egress cost, and doubling the computational load on the API without providing a single byte of new acoustic information to the neural network.
Exactly. It's useless bloat. Plus, Google's speech-to-text API is already pre-trained on massive datasets of native 8 kHz telephony audio. It understands the specific acoustic degradation of phone calls. The architectural mandate is to feed the API the raw, unadulterated data.
Okay, that covers the audio quality. And the second constraint in this scenario is the length of the file. 5 minutes of audio. The blueprint requires the engineer to use asynchronous recognition, specifically the long-running recognize API method.
Right. If you attempt to send a 5-minute audio file using a standard synchronous API call, you are demanding that the HTTP connection remain open for the entire duration it takes the neural network to process the speech.
Which is a long time in computer years.
Network protocols are designed to drop idle or long-running connections to prevent server overload. A synchronous call will almost certainly time out, crashing your pipeline.
So the connection just dies.
Yes. The long-running recognize method is asynchronous. You upload the audio to a cloud storage bucket, send a lightweight API request with the file's location, and the API instantly replies with an operation ID, basically a ticket number.
Like at the deli counter.
Exactly like that.
Yeah.
Your server closes the connection, does other work, and occasionally polls the API using that ticket number until the transcribed text is ready.
This decoupled asynchronous architecture allows you to string multiple APIs together into highly complex analytical pipelines. It's like digital Lego. You don't need to know how to build a voice recognition engine from scratch, you just need to know how to connect them. We see this in another scenario where the goal isn't just to transcribe the 5-minute call, but to extract the emotional sentiment of the customer. Are they angry? Are they satisfied?
A very common use case.
The required architecture is to use that asynchronous speech API to generate a raw text transcript and then instantly route that text payload into an entirely different service, the natural language API, utilizing its analyze sentiment method.
It's amazing when you think about it. 10 years ago, extracting emotional sentiment from raw audio required a team of specialized data scientists to build an acoustic model, a language model, and a classification model, all from scratch.
And now,
Now, it is achieved by chaining two API endpoints together. The engineering challenge has shifted from algorithmic design to system orchestration.
but the blueprint also highlights the limitations of these pre-trained generalized APIs. Let's look at the Vision API. There is a scenario where a community forum for pet owners needs to automatically detect if uploaded photos actually contain animals.
Okay.
The goal is near real-time detection with the lowest possible cost. The correct choice is to ping the Cloud Vision API and use standard object localization.
Because identifying a dog or a cat in an image is a universally solved problem.
Yeah.
Google has trained the Vision API's foundational models on billions of images.
So it already knows what a dog looks like.
The neural network already possesses the latent embeddings required to recognize the geometry and texture of a golden retriever. Sending the image to the API returns an instantaneous JSON payload detailing exactly what objects are in the frame and their bounding box coordinates.
But contrast that with a scenario involving an auto insurance company. They need an application to analyze photos of car accidents and automatically infer which specific car parts are damaged. The blueprint explicitly rejects using the standard Vision API for this. Instead, it requires the engineer to train a custom object detection model in AutoML using a proprietary dataset of annotated insurance photos. Why does the API fail here?
It fails due to a lack of domain specificity.
Domain specificity.
Right. The standard Vision API is incredibly intelligent, but it provides generalized classifications. If you send it a photo of a crashed vehicle, it will successfully return labels like car, accident, or tire.
Which isn't helpful for a claims adjuster.
It's exactly. However, the insurance company's business logic requires the system to mathematically differentiate between a scratched 2018 Honda Civic front bumper and a dented right quarter panel. The foundational model does not possess that highly specific, industry niche visual vocabulary.
So you turn to AutoML. You upload thousands of historical claims photos where human adjusters have meticulously drawn bounding boxes around specific damaged parts.
And AutoML utilizes transfer learning.
What does that mean?
It doesn't start from scratch. It takes a massive, pre-trained neural network that already understands how to detect edges, shapes, and lighting gradients, and it freezes those foundational layers. It only retrains the final classification layers of the network using your specific annotated insurance data.
Oh, that's clever.
You bootstrap the intelligence of a massive model and focus its attention entirely on your proprietary business problem.
This exact hybrid approach is mirrored in text processing, too. We have a scenario where a multinational corporation needs to translate highly specific Spanish legal and business contracts. The generic translation API might struggle because a casual Spanish phrase could have a very rigid, legally binding definition in a corporate context.
Right.
The blueprint dictates a fascinating two-step process. First, use the standard Google Translate API to rapidly generate thousands of translated phrase pairs to create a baseline. Then, use those phrase pairs to train a custom AutoML translation model.
It perfectly demonstrates that the architectural choices are rarely binary. You don't have to choose between a fully generalized API and building a custom model from scratch.
You can mix them.
The optimal engineering path is often to leverage the massive scale of the API to automatically generate your initial dataset, and then use AutoML to fine-tune that dataset so the resulting model inherently understands your specific corporate dialect.
Okay, let's pause here because this is where the theory violently collides with reality. We have successfully prepared our data, selected the optimal training infrastructure, and integrated our APIs. We have built an operational machine learning model.
The easy part is over.
Right. But how do we mathematically prove that the model's decisions are actually useful, fair, and safe for human interaction? Because a high accuracy score on a dashboard can be a complete illusion.
Oh, absolutely.
This is addressed in a scenario dealing with the accuracy paradox. An engineer builds a binary classification model to scan thousands of documents and detect whether a specific company logo is present. The beta set is extremely skewed. 96% of the documents do not contain a logo. The blueprint states that relying on accuracy as the primary metric here is a critical failure. It mandates evaluating the model using the F1 score.
To understand why accuracy fails here, you have to look at the baseline probability. If I write a hard-coded script that doesn't use machine learning at all, a script that simply outputs the text "no logo detected" for every single document it processes, that completely blind script will be correct 96% of the time on this dataset.
Because 96% of the time, there is no logo.
Exactly. I could present that script to management and claim I built an AI with 96% accuracy. But the model is entirely useless because it failed to identify a single actual logo.
It's just a parrot saying no.
Yes. When dealing with highly imbalanced data sets, whether you are detecting fraud, rare diseases, or logos, overall accuracy is a deceptive vanity metric. You must decompose the model's performance into precision and recall.
Let's clearly define those because they really govern the underlying logic of every ML system.
Sure, precision is a measure of the model's exactness. It asks, out of all the documents my model claimed had a logo, how many actually did?
Okay.
If a model flags 10 documents and only 5 of them actually have logos, the precision is 50%. It suffers from false positives.
You cried wolf.
Exactly. Recall, on the other hand, is a measure of the model's completeness. It asks, out of all the actual logos hidden in the total dataset, how many did the model successfully find?
Got it.
If there are 100 logos hidden in the pile and the model only finds 20 of them, the recall is 20%. It suffers from false negatives.
And the F1 score, where does that fit in?
The F1 score is the harmonic mean of precision and recall. It mathematically punishes a model that has a severe imbalance between the two. You can only achieve a high F1 score if the model is both highly precise in its claims and highly capable of finding the vast majority of the target objects.
So it's a much harder test to pass.
It is the only metric that proves the model is actually identifying the underlying pattern rather than just blindly guessing the majority class.
And tuning the balance between precision and recall isn't just an abstract mathematical exercise. It translates directly to human consequences and business liability.
Without a doubt.
There is a scenario regarding a model deployed to detect fraudulent credit card transactions. The prompt explicitly states that failing to detect a fraudulent charge is catastrophic for the cardholder. The current model is failing to catch many of these fraudulent transactions. The blueprint dictates that the engineer must actively decrease the model's classification threshold. Walk me through the mechanics of a threshold and why lowering it solves the problem.
So a binary classification model doesn't just output fraud or not fraud. It outputs a probability distribution. It analyzes a transaction and outputs a score, say 0.85, meaning it is 85% confident the transaction is fraudulent.
Okay.
The threshold is the mathematical line in the sand the engineer draws to convert that probability into a binary action. The default threshold is usually 0.5. If the model is 51% confident, it flags the account. If it is 49% confident, it approves the transaction.
But the business constraint here is that we cannot afford to miss any fraud. A false negative letting a hacker drain a bank account is an unacceptable outcome.
Therefore, you manipulate the threshold. You lower it from 0.5 down to, say, 0.15. Now, if the neural network analyzes the telemetry and determines there is even a 15% probability that the transaction is anomalous, it triggers the fraud protocol.
By lowering the threshold, you cast a massively wider net.
You drastically increase your recall. You guarantee that almost zero actual fraud slips through the system.
It's exactly like a smoke detector. I'd much rather it go off when I burn toast a false positive than stay silent when the kitchen is actually on fire, a false negative. But mathematically, there must be a severe penalty for casting a net that wide.
Oh, there is. The penalty is the destruction of your precision. Because the model is now hypersensitive, it will flag thousands of perfectly legitimate transactions simply because a user bought a coffee in a different time zone.
So you generate a massive wave of false positives.
Yes.
I understand the logic in theory, but in practice, you are infuriating thousands of your own customers by freezing their cards unnecessarily.
It is an engineered trade-off. You are making a calculated decision that the friction of a customer having to reply yes to an automated SMS text message to unfreeze their card is vastly less damaging to the business than the financial and reputational ruin of allowing a hacker to steal their identity.
We see the inverse of this logic applied in an industrial manufacturing scenario, too. An engineer is building a model to predict machine failure on a factory floor. The prompt states that scheduling regular maintenance checks is relatively cheap, but a total unexpected machine breakdown costs the company millions and halted production.
So again, false negatives are the real enemy.
Right. The engineer is presented with several models and must choose one based on its metrics.
And the architectural mandate is to select the model with the absolute highest recall, provided that its precision remains above a floor of 0.5.
Because, just like the fraud scenario, missing a failing machine is the worst-case scenario. You want high recall to catch every vibration anomaly. You are willing to accept the false positives, meaning you will frequently dispatch a mechanic to inspect a machine that turns out to be perfectly healthy because the cost of that mechanic's time is trivial compared to a factory shutdown.
Right.
But why put a floor on the precision at 0.5? Why not push recall to maximum?
Because if precision drops below zero point 0.5, it means that more than half of the alerts the model generates are false alarms.
And people hate false alarms.
At that point, you induce alert fatigue. The mechanics will spend their entire shift chasing phantom issues, they will stop trusting the system, and they will begin ignoring the alerts entirely. The engineer must mathematically balance the threshold to maximize safety without destroying the operational efficiency of the human workforce.
This profound responsibility over the model's behavior directly extends to the issue of bias, too.
That's a huge one.
There is a scenario where a deployed ML model is actively underperforming when predicting outcomes for certain demographic subgroups. The prompt clarifies that this failure is due to severe class imbalances in the historical training data, but adds a really harsh constraint. The engineering team cannot collect any new data.
This is a ubiquitous failure mode in machine learning. If you train a facial recognition system or a loan approval model on a data set that predominantly features one specific demographic, the neural network will optimize its weights and biases to serve that majority group.
It just ignores everyone else.
It mathematically neglects the minority subgroups because errors made on those small groups don't significantly impact the overall loss function during training. It is a mathematical failure that manifests as real-world discrimination.
If the engineer is forbidden from gathering more diverse data to fix the imbalance, how does the blueprint dictate they solve this computationally?
The blueprint offers two mathematical interventions: upsampling the data or reweighting the loss function.
Let's start with upsampling.
Upsampling is a data-centric approach. You algorithmically duplicate the existing examples of the minority subgroup within the training data set.
Just copy and paste?
Essentially, yes. If a specific demographic only makes up 5% of your data, you synthetically replicate those rows until they constitute 20% or 30% of the training batches. You are violently forcing the neural network to confront and learn from those examples more frequently during its gradient descent iterations.
And what about reweighting?
Reweighting is an algorithm-centric approach. During training, a neural network uses a loss function to calculate how badly it failed on a prediction, and it updates its internal math to prevent that failure in the future. Reweighting involves manually modifying that loss function.
Like changing the score of a game?
Kind of. You program the system to say, if you make an error predicting the majority class, the penalty is 1 unit. But if you make an error predicting the minority subgroup, the penalty is 10 units.
You mathematically force the algorithm to care exponentially more about accuracy within the underrepresented group.
It's engineering equity directly into the math.
We see a proactive defense against this in a scenario regarding targeted advertising. An engineer is pulling historical logs to build a training dataset, and the goal is to prevent unfair bias from creeping into the model. The required methodology is to collect a stratified sample of the production traffic. Walk me through the mechanics of stratified sampling and why a purely random sample is dangerous.
Okay, if you possess billions of rows of user logs, you obviously cannot train on all of them. You must take a sample. If a specific demographic group represents exactly 1.5% of your total user base, and you execute a purely random 1% sample of the database, statistical variance dictates that you might randomly miss that entire 1.5% demographic.
Just by bad luck.
Yes. They could be completely excluded from the training data simply due to the luck of the draw.
They just disappear from the model's understanding of reality.
Precisely. Stratified sampling intervenes in the randomization process. It forces the sampling algorithm to respect the overarching demographic proportions.
How does it enforce that?
It dictates, analyze the entire population, identify the specific subgroups, and guarantee that the final extracted sample contains exactly 1.5% of this specific demographic. It mathematically ensures that the training dataset is a perfect micro-reflection of the macro population, preventing statistical variance from erasing minority groups.
And ensuring a model is fair goes hand in hand with ensuring it is explainable. As models become more integrated into critical infrastructure, stakeholders and regulatory bodies demand to know why an AI made a specific decision. Neural networks are notoriously opaque. They are black boxes of millions of interacting weights. There is a scenario where an engineer deploys a deep learning model to analyze high-definition images of concrete bridges to predict structural defects. The stakeholders demand visual proof of why the model predicts a bridge will fail. The blueprint mandates using TensorFlow paired with the integrated gradients method. How does this technique force a black box to explain its visual reasoning?
Integrated gradients is a profound mathematical technique for attributing a neural network's prediction back to the original input features, in this case, individual pixels.
Okay, how does it work?
Imagine the model analyzes a photo of a bridge pylon and outputs a 90% probability of structural failure. The engineer needs to know which specific cluster of pixels caused the model to spike to 90%. Integrated gradients works by establishing a baseline. It feeds the model a completely blank, black image.
Okay.
The model obviously predicts a 0% chance of failure.
Because there's no bridge. The baseline is absolute zero.
Then, the algorithm generates a sequence of images, slowly fading the actual photo of the bridge in from black, step by step, until it reaches full resolution. At each microscopic step of the fade-in, the algorithm calculates the gradients, the partial derivatives.
That sounds intense.
It measures exactly how much the model's internal prediction score changes as each individual pixel gets slightly brighter.
Oh. It is essentially monitoring the neural network's brain activity, watching which specific neurons fire as the image slowly comes into focus.
Yes. And by mathematically integrating or summing up all of those microscopic gradient changes across the entire fade-in process, it produces a highly precise attribution map.
A map of what?
It generates a visual heat map overlaid on the original photo that violently highlights the exact pixels that drove the prediction. It can circle a microscopic hairline fracture in the concrete and definitively state, these 40 pixels are the mathematical reason I predicted a failure. It translates billion-parameter matrix multiplication into a visual argument that a human structural engineer can actually verify.
Which bridges the gap perfectly to our final operational reality. We have wrangled the data, trained the architecture, tuned our thresholds, and guaranteed our mathematical lineage can be explained.
It's quite a journey.
But deploying a Jupyter Notebook on a laptop is a science experiment. Operating that model continuously for millions of users without the system tearing itself apart requires an entirely different discipline.
It requires MLOps machine learning operations.
Mhm.
It is the rigorous application of traditional DevOps software engineering principles to the inherently unstable, probabilistic world of machine learning.
A massive pillar of MLOps in this blueprint is tracking and lineage. There is a scenario where an enterprise team is deploying dozens of models across multiple Google Cloud projects. The required architecture to maintain order is the integration of Vertex AI Pipelines, Vertex AI experiments, and specifically Vertex AI ML metadata. What physical function does the ML metadata service perform in a distributed pipeline?
ML metadata functions as the immutable ledger, the unalterable flight recorder for your entire machine learning factory. Every time a dataset is ingested, every time a pre-processing script executes, every time a hyperparameter is tweaked, and every time a model artifact is compiled, the ML metadata service automatically captures the exact event.
It logs everything.
It records the timestamp, the identity of the engineer, the precise git commit hash of the code used, and the cloud storage URI of the exact dataset snapshot.
It creates a permanent cryptographic chain of custody for the model. But why is this extreme level of surveillance necessary? We see it emphasized again in another scenario, requiring engineers to prove the lineage of a custom model in production using a batch predict component. Why the obsession with backward traceability?
Two fundamental reasons: auditing and debugging. Consider a scenario where a regulatory agency audits your financial institution because your newly deployed loan approval model is suddenly exhibiting severe demographic bias.
That'll be bad.
You cannot simply tell the regulators, the neural network learned it. You are legally required to prove exactly how the model was created. With ML metadata, you can trace the live model's lineage backward.
Step by step.
Yes. You start at the prediction endpoint, trace back to the specific compiled model artifact, trace that back to the exact Vertex AI training pipeline run, trace that back to the specific pre-processing script, and trace that all the way back to the exact snapshot of the data warehouse that was queried on that specific Tuesday at 2:00 p.m.
Wow, so you can recreate the exact physical conditions of the laboratory at the moment the model was born.
Exactly. And for debugging, another scenario highlights using this metadata, loading it programmatically into a pandas data frame, and plotting it with matplotlib to visually compare the performance metrics of version 3 of a model against version 4. It transforms machine learning from a series of ad hoc experiments into a rigorously auditable engineering discipline.
But MLOps is also about raw infrastructure power. There is a scenario regarding a team developing highly complex TensorFlow financial models. They need to drastically reduce the time it takes to train these models, but they also require the ability to interactively debug the code line by line.
A very demanding team.
Very demanding. The blueprint dictates configuring a V38 TPU VM and using SSH to log directly into it. Let's break down the hardware. What is a TPU, and why does its physical architecture make it superior to a standard CPU or GPU for deep learning?
Well, a TPU, or Tensor Processing Unit, is an application-specific integrated circuit designed by Google. A standard CPU is a highly versatile generalist. Its architecture is designed to rapidly switch between checking network packets, rendering a user interface, and executing logic gates.
It does a bit of everything.
But neural networks do not require versatility. A neural network is fundamentally just billions of matrix multiplication operations executed in parallel.
It is just massive grids of numbers being multiplied by other massive grids of numbers.
Exactly. A TPU discards all the general-purpose architecture of a CPU. It is built around a massive systolic array, a physical grid of thousands of arithmetic logic units hardwired together.
A systolic array.
Yeah, when data flows into a TPU, it physically ripples through this dense grid of multipliers in a continuous wave, executing millions of calculations per clock cycle without constantly reading and writing to memory registers. It is a hypercar built exclusively for linear algebra.
But historically, utilizing TPUs required sending massive compiled payloads over a network to a remote cluster. If the code broke, debugging was a nightmare of reading remote error logs. The breakthrough in this scenario is the TPU VM.
Yes, the TPU VM architecture attaches a fully functional virtual machine directly to the physical TPU hardware on the motherboard.
So you're right there on the hardware.
By allowing engineers to SSH securely log in directly to that virtual machine, they can open their Python environment, set interactive breakpoints, and execute their TensorFlow code step by step while sitting directly on top of the supercomputer. It merges unfathomable computational scale with the immediate tactile debugging experience of working on a local laptop.
But the infrastructure challenges don't end at the training phase. The physical architecture of live inference is equally critical. There is a nightmare scenario for an e-commerce platform. An ML engineer builds a brilliant model that predicts which specific discount coupon to offer a user at checkout to maximize conversion.
Okay, good so far.
The model's logic is perfect. However, the front-end web team reports that the model is returning predictions so slowly that the checkout page is hanging for several seconds. Users are abandoning their carts.
Latency is killing the business.
Exactly. The prompt reveals that the current pipeline queries a BigQuery table in real time to grab the user's historical purchase behavior, feeds that history to the model, and generates the prediction.
And this is a classic architectural mismatch. BigQuery is the wrong physical tool for the job.
Which sounds contradictory because earlier we established that BigQuery is a miraculous tool that can scan petabytes of data in seconds for our analytics. Why is it suddenly the bottleneck here?
Because latency and throughput are different physics. BigQuery is optimized for massive analytical throughput. If you ask it to scan 10 years of sales data and calculate a complex aggregation, it spins up thousands of distributed workers and returns the answer in 5 seconds.
Yeah.
That is miraculous for a data analyst. But 5 seconds of latency on a live checkout page is an absolute eternity. A live web application requires OLTP architecture. It needs to retrieve a single row of data in less than 5 milliseconds. Using BigQuery to fetch a single user's history during a live web request is like using a massive freight train to deliver a single pizza.
The overhead of initializing the query takes longer than the actual computation. The blueprint solution is to decouple the analytical storage from the serving storage. It mandates pre-computing all of the historical behavior in BigQuery beforehand, but then exporting that data and attaching a low-latency database like Cloud Bigtable or a memory store Redis cache directly to the model endpoint.
Memory store stores data entirely in RAM, rather than on physical disk drives. When the user hits the checkout page, the web application queries the in-memory database, retrieves the historical profile in less than a millisecond, feeds it to the model, and the coupon is rendered before the user's eye can even register the page load.
The ML engineer must realize that their neural network is merely one cog in a much larger, time-sensitive software ecosystem, and an ecosystem that must eventually heal itself. Our final scenario encapsulates the ultimate goal of MLOs. An engineering team deploys a Vertex AI pipeline utilizing an AutoML translation model to automatically translate technical instruction manuals for scientific equipment. But language is organic. It drifts.
Languages always change.
Over time, new scientific terminologies are invented and phrasing evolves. The model's accuracy will inevitably degrade as the live text begins to diverge from the text it was originally trained on. The architectural mandate here is to deploy the endpoint with model monitoring enabled, which automatically triggers a retraining pipeline when data skew is detected.
This is continuous training. It is the realization that a machine learning model is never truly finished. When you deploy a model monitoring service, it sits silently alongside your live endpoint, just watching. It mathematically compares the statistical distribution of the live text data flowing in from the users against the statistical distribution of the baseline data the model was originally trained on.
It's calculating the mathematical distance between the past and the present.
Exactly. When the monitoring service detects that the live vocabulary has drifted beyond a predefined statistical threshold, meaning reality has fundamentally changed, it fires an alert. But it doesn't just page an engineer.
It fixes itself.
It automatically triggers the Vertex AI pipeline to wake up, pull the absolute latest historical data from the warehouse, spin up the compute clusters, train an entirely new AutoML model from scratch, evaluate its performance, and if it exceeds the old model, seamlessly swap it into the live endpoint.
You aren't just deploying a static algorithm. You're deploying an autonomous factory that constantly monitors its own degradation and automatically manufactures a smarter version of itself when the environment changes. That is a massive paradigm shift.
It is the pinnacle of MLOps.
We have covered an immense amount of ground today, transitioning from raw, messy data all the way to a self-healing, automated AI factory. Let's synthesize the core philosophy a listener should extract from this deep dive into Google's engineering brain.
Well, the overarching theme is the relentless pursuit of pragmatic scale. The blueprint demands that engineers prioritize managed services, leveraging BigQuery ML for structured data or pre-trained APIs for unstructured data to eliminate unnecessary code and reduce operational overhead. You only write custom TensorFlow code when you hit extreme hyperscale constraints that demand bespoke optimization.
And data integrity.
Furthermore, you must aggressively defend the integrity of your data. You respect the physics of time series data with strict chronological splits to prevent leakage, and you utilize immutable computational graphs via TensorFlow transform to eradicate train-serve skew.
And beyond the code, it requires a profound ethical and operational responsibility. You must recognize that a high accuracy score on a dashboard can be mathematically deceptive, and you must tune your thresholds to balance precision and recall based on the actual human consequences of a false positive versus a false negative.
That's vital.
You must actively engineer fairness into your loss functions and sampling techniques, and utilize tools like integrated gradients and ML metadata to guarantee that your AI remains transparent, auditable, and firmly under human control.
It is the evolution of data science into hardened industrial software engineering.
We have spent this entire discussion analyzing how engineers adapt models when they encounter skew, relying on pipelines that ingest fresh human data to correct the AI's understanding of reality. But I want to leave you, our listener, with a final architectural reality to consider. We are rapidly entering a phase where AI models are generating a massive compounding percentage of the text, code, and imagery that populates the internet.
A profound and, frankly, destabilizing inflection point for data engineering.
Indeed. So consider the mechanics of the continuous training pipelines we just discussed. In the very near future, when an autonomous MLOps pipeline wakes up to ingest the latest data from the web to refresh its understanding of the world, it will inevitably be ingesting and training on synthetic data that was generated by other AI models. It creates an infinite feedback loop.
Which is terrifying.
How will the ML engineers of tomorrow design architectures that can prevent model collapse, the mathematical phenomenon where an AI gradually amplifies its own synthetic hallucinations and forgets the complex nuances of original human reality simply because the human signal is buried under a mountain of artificial noise? How do you maintain the integrity of the data foundation when the world itself becomes synthetic?
That is the defining architectural crisis that the next generation of machine learning engineering will have to solve.
It certainly is. And it brings us right back to the realization that the deterministic comfort of traditional software is gone. The systems are probabilistic, the data is alive, and the engineering required to keep it stable is incredibly complex. But hopefully, by unpacking this architectural blueprint today, we have equipped you with the conceptual tools needed to navigate those systems. Thank you for joining us on this deep dive. Keep analyzing the architecture, keep questioning the metrics, and we will catch you next time.